David Spears, civil engineering instructor at Texas Tech University, talking about solids CE 3303, exam number 2, page 4, a statically indeterminate torsion problem. This is a composite of the 3 versions of the test. I have a solid steel shaft, ACB, of diameter 50 millimeters with a shear modulus of 75 gigapascals with a torque applied at point C of 400 Newton meters. The thing's a meter long in 2 sections, 300 millimeters at this end, at the A end, 700 millimeters long at the B end. You were asked for a compatibility equation to help solve this because it is statically indeterminate. Got 1 moment equation and 2 unknowns. So the key to this was recognizing that the twist at point C due to from A to C has got to be equal to the twist from B to C, because these ends, each end A and B, are fixed, so there's no twist relative to each other. So it's going to twist one direction and then twist back the other direction due to the other torque. So the equation looks like this: the twist at AC, phi, minus the twist at CB is equal to 0. So phi AC is equal to phi CB. Twist, we know, is torque times length divided by JG. Now I need to go over, you were not asked for this equilibrium equation, but it's vital to solve the problem. I cut 2 little sections. First I do a big free body of the thing, and I put a torque at A and a torque at B in the same direction, resisting the 400 Newton meter applied torque. I'm just assuming something, and assuming both of them in the same direction opposite this, and I'll let my signs tell me whether or not I'm right or not. So my equilibrium equation is I sum moments about the x-axis, which is the longitudinal axis for the shaft. That's equal to 0. So TA minus 400 Newton meters plus TB is equal to 0. Cut a little section, free body diagram 1, just to the left of point C, and my forces there are TA, the unknown, and an internal force in the opposite direction of negative TA. And I cut a free body just to the left of point C, and I have the applied force 400 Newton meters applied, TA resisting it at the A end, and then an internal torque of 400 minus TA, which has also got to be equal to TB at this end. So now I know TB is equal to 400 minus TA. So I'm going to go back up to my twist equations. I'm going to say the torque at A, times its length of that section, 300 millimeters, divided by JG, has got to be equal to the torque over this section, which is 400 minus A, or TB, times 700, its length, divided by JG. I can eliminate the common terms of JG, and I get TA times 300 is equal to TB times 700. Therefore, TB is equal to 300 over 700 times TA, or 0.4286. Now I can use that value and substitute back into my equilibrium equation, which is TA minus 400 plus TB is equal to 0. So TA minus 400 plus, substituting 0.4286 TA in for TB, get this equation. Combining the terms of TA, I get 1.4286 TA is equal to 400 Newton meters. TA is therefore equal to 280 Newton meters, and TB is 0.4286 of that, so it's 120 Newton meters. I'll use that here. No, I won't use that here in a second. Then I was asked, what's the twist in section AC on the left end? That's the torque times the length divided by JG. Got to get my units correct. 280 Newton meters times 1,000 for millimeters per meter times 300 millimeters long divided by J, which is pi over 2 times the C radius to the 4th power. It's pi over 2 times 25 to the 4th. That's millimeters to the 4th. And the shear modulus is 75 gigapascals, which is 75,000 megapascals. A megapascal is a Newton per millimeter squared. So I get my units: Newton millimeters squared divided by Newton millimeters squared. So this is dimensionless radians. The number is 0.00183 radians. I'm almost done. I want to know the maximum shear stress due to the torsion in section AC. So that's the simple formula. Tau is equal to T rho over J. My torque is 280 Newton meters times 10 to the third puts it in Newton millimeters. Rho is the radius, 25 millimeters, divided by pi over 2. I'm missing my 2 down there. Times 25 to the 4th, which is J. Checking my units, I come up with Newton millimeters squared over millimeters to the 4th. So I get the number 11.41 newtons per millimeter squared, which is a megapascal. So the answer is 11.41 megapascals.